Merci. OK, vous m'entendez bien? OK, merci pour... oh, no, I speak in English. So thanks for the invitation. I am going to speak... So I am a professor at the Center for Processes, Renewable Energies and Energy Systems of École des Mines. Our center is located at Sophia Antipolis in the south. I have been active in the area of renewable energy forecasting for more than 30 years, actually. I did my PhD many years ago on that. And I will speak today about the state of the art on renewable energy forecasting and latest tendencies of research and challenges, because the workshop here is about challenges that we can resolve with mathematical modeling, etc. So I can give at the end a list of challenges that can be the starting points for future research and research activity. So I will start with a context. I will present the evolution of the state of the art in renewable energy forecasting. Afterwards, I will present a European project that we have coordinated lately, Smart4S, some highlight results and the challenges. So today, everybody knows, I think, well, you are aware of that, our power systems evolve in the context of energy transition. There is a large-scale integration of distributed sources, which can be renewable, storage, demand response, power to X, X to power, and other options. The connection of all these sources to the networks involves a flow of information which is generated, which on the one hand is a challenge, but on the other hand, it is this that enables the possibility to manage all these sources and in an economic and secure way. So globally, the power system evolved to a highly complex and interacting system. And here on the right, you can see the representation, which is quite standardized, of what is a smart energy system, a smart grid today. At a lower level, we have the infrastructures, the assets, the hardware. Then we have the communication layer that permits to all the assets to communicate. And the information layer. And then we have the functional layer, where we have all the functionalities that permit to manage the system for different actors. So this is the business layer. So we can have other functionalities for a system operator, for an aggregator, for a trader, etc. So it's very important to have efficient solutions for this intelligence layer. And today we have new challenges, because we have crises, we have the climate change with more frequent extreme events. So all these functions have to be resilient to all these challenges. So some example of functionalities. Actually, Sylvain gave some before, like trading. So first is the capability to forecast the demand and the generation, especially from the weather-dependent renewables, dynamic line rating, and other functions. To do the scheduling of the units, to decide when we will operate each unit in time. This is for system operators. For transmission system operators like RTE, for example, to decide how to allocate an optimal level of reserve so that they can manage events or problems in the network. For distribution system operators, sometimes we have a lot of, for example, photovoltaic production that we cannot, and we have congestions we cannot use, so they have to predict this and to manage this kind of congestions in the grid, in the distribution grid. We can have hybrid systems like we have today in islands like Corsica, etc., where we can have renewables, photovoltaic or wind coupled with storage, for example, or electrolyzers. When we are an aggregator, we can manage a portfolio of assets, wind farms, PV plants, and try to optimize the way we participate in electricity markets. And we have a lot of markets today, day ahead, intraday, ancillary services, local flexibility, etc. And control of assets, predictive management, etc. Here we are interested in functionalities that try to optimize the decisions we take a few minutes to days ahead. And this is what I have highlighted mainly here in green. And if we come back to the renewables, okay, today we have objectives to integrate a lot of renewables in the power systems. However, the production is highly variable. On the left, we can see the production of a wind farm, and we can see that it's hourly production for 1 month, and we can see that the power can variate quite rapidly from 0 to 100% of the capacity. And on the right, we have the profile of a photovoltaic production where we can have of one plant, where the passage of clouds can result to very high intraday variations, for example, which are, all these represent challenges for the system operators. So what is the role of forecasting in this? If we want to optimize the decisions we take in the next horizons, it's important to have the capacity to predict what will be the production of wind, solar, and all these variable resources. So the first solutions appeared in the literature quite a long time ago for wind forecasting, because we started first to install wind farms. And yeah, so in the first model that's reported in the literature was 1985. And then forecasting solutions were tools, etc., systems were used by the system operators, etc., especially from the early 90s, especially in the countries where, for example, were pioneering development of wind power, like Spain, Denmark, Germany. However, despite this maturity that today most system operators use forecasting system or services operationally, large forecast errors may occur, and they may have a high financial impact or technical impact. And improving forecasting accuracy is actually a continuous requirement by end users, the system operators, etc. And also the fact that we are in a system that we have all the time new technologies and solutions and business models developing, etc. There is a requirement to develop continuously new forecasting solutions, products. Here on the left, we see a typical forecasting, day-ahead forecasting of wind production for 2 days, actually, which is probabilistic. So here the product is to predict the power output of a wind farm every hour, and then the uncertainty which is associated to this prediction. And we have the similar for the day-ahead forecast of PV on the right. So the general principle of forecasting, why it was, I guess, well, you have seen a lot of information about this. For wind, usually we use measurements of the plants, and also numerical weather predictions and information about the terrain. And as a function of the horizon, can be only measurements or combined with weather forecasts. Today we can use also other source of information like LiDAR or radar or other information. And then we have a forecast model that can be either a physical one, can be statistical, can be neural network or whatever, artificial intelligence based. And then we have this typical probabilistic forecast. For solar forecasting, I would say the situation is more complex because the users of the forecast have many applications. They may need forecasts for the short term to manage a storage, or to participate for the next hours, or to participate in the intraday market for the next 6 hours, or the day-ahead market for the next day, etc. So what we see in the literature today is that as a function of the data that are available, we develop dedicated models. So for example, as we saw actually before, if we have sky cameras and maybe local measurements, then we use them in a model, and we make able to make predictions for the next, let's say, period of up to 1 hour or 30 minutes or so. Then if we have geographical distributed data, then we have a family of models which are called spatiotemporal and they try to exploit the geographical distributed characteristics and correlations and propagation of the phenomena. And then we can have models up to 6 hours ahead. When we integrate satellite images, then we can they have a capacity to predict up to 6 hours ahead or so. And then numerical weather predictions, depends on the model, they can go up to 10 days ahead, actually. Generally, today we have, we provide to the operators with different models that exploit each source of information. So if I, well, it's something that I show quite often, just to show how a technology evolves. It's quite interesting. Also for those who want to use the models and also who want to work on this research. So as I mentioned before, for wind forecasting, the first models appeared in '85. It was a purely autoregressive model for power production. Then between 90 and 2000, it was the period where wind energy was developed in Germany, Denmark, etc., also in islands. And then we started to see the first statistical approaches with different models, also physical modeling, where they try to model how the wind flows on the terrain and take into account the terrain complexity. It was the moment when we saw the application of the first methods based on artificial intelligence. And also at that time, there was a first application where we used numerical weather predictions as input to predict wind power. You know, the output of the meteorologist as data input. And there were the first hybrid operational models that were used by the operators. Yeah, at that moment, actually, was also the first time that artificial intelligence neural networks were applied in the field of renewable energies, actually, for wind power forecasting. It was a paper in the frame of the research we were doing at Coldemin. And then by 2000, we tried to in our laboratory to develop some research projects to federate all the efforts that were done at European level, because at that moment the research was mainly in Europe, in order to give a boost actually to this technology, because the need was very important. So these were very big projects of 20, 25 partners that involved a lot of system operators, etc. And the first one was Anemos, that developed, tried to compare and set protocols for evaluation of the models, more advanced physical modeling, statistical models, methods. At that time, the buzzword was data mining for artificial intelligence, etc. Now nobody uses this word, but CNN, neural networks, etc., were data mining. It was the big work. Then what we found, and it was very important, is that actually when we were comparing models, none of them was the best. Well, some were very bad, but when those that were good, we could not say that was, for example, I don't know, feed-forward neural network or ARMA models that were the best. But we saw that, okay, if we would combine different models, the combination gave better results, actually. And this may come from different skill of the models, or because the different models were using different sources of input, actually, and they were exploiting this complementary information. And this actually became the mainstream approach, and the first operational system that was implemented by the system operator of Spain, Red Eléctrica de España, was based actually on this combination approach, and today it's used by several actors. Then in some follow-up project, like Anemos Plus and SafeWit, we try to develop more advanced tools to go beyond the classical probabilistic forecasting. And then we had some approaches, some new products actually, and behind each one there is quite a lot of research. So, for example, there was the time that we developed the first spatiotemporal approach, where we were trying to use to consider that the data from neighbor wind farms were giving information to improve the prediction of a specific wind farm. So the neighbor wind farms were used as sensors, because if we observe some error or at some distance, then this propagates, and this can be a predictor for what happens in our wind farm. Also, there was a demand, for example, to develop ramp forecasting to predict the abrupt and severe variations of wind power in a probabilistic way. So we were predicting, for example, the probability that a ramp is coming and the magnitude of the ramp, and this is this is a different product. And also, based on ensembles and scenarios, we derived risk indices, and this for the situation that at some point we cannot do much with weather forecast. I mean, everybody knows that it can happen that tomorrow we predict good weather and we have rain. But this can be expressed by the ensembles, because in that situation, the ensembles we get by Met of France or other institutes are scenarios for tomorrow with a very big spread. They can predict very different situations. And then if we evaluate this spread, we can define some risk indices about what is the confidence we can have for the next day, about the predictions. So if the spread is very small of the sample, we have confidence that, okay, tomorrow we predict good weather and we are going to have good weather. However, if the spread is low, very high, then we predict good weather, but tomorrow we can't have anything actually. So this, we don't try to improve the prediction, but we try to give additional information that can be used to adapt the decisions we take about the management of the power system today and be more or less conservative. Also, there are other tools like to, when we detect an error at some area, to develop some alarming tools that we can have a level of error, etc. So solar power forecasting, actually, the first paper, etc., appeared quite later, much later, in around 2008-9, and they benefit a lot of the advance and the experience of wind forecasting. So this technology evolved very much more quickly, not in a very much incremental way as wind. And then came Smart4S, the last project, where we tried to develop a lot of data science approaches and quite new approaches. I will show some concepts later. If we want to express this as a function of the publications, how the literature evolved, we did a kind of bibliometric analysis in Scopus of the mainly journal papers or the publications which are in Scopus. And we see that we start, okay, with very negligible amount of publications by 85. Then when we have these European projects, it's the moment where mainly we had research in Europe, and these 3 European projects, we had some like 240 papers in conference and journals. And nowadays there is an international interest, and there are some like 600 papers per year for wind and solar forecasting. So it's an area which is very challenging, very competitive. And we can see this curve is the papers which are related with artificial intelligence. So we can see that there is a lot of kind of explosion also of the publications which are based on AI. And especially in the last years, there are lots of methods applied, papers applying deep learning, like the methods that presented Sylvain previously. So, given all this amount of papers, etc., what is the new that we can do today? I mean, what can we imagine that we can do as research? Some people, when we go to some organizations to support our research, they say, okay, but nowadays everything is done. I mean, what you can do on forecasting. So this is not very good, because we are very imaginative and we can find always new. So this European project, which is not new anymore, was a common effort by 13 partners from 7 countries. Actually, it was concluded last year, but still we have some activity, publications, etc. And here, the idea was to develop a kind of holistic view of forecasting. Here on the left, I show the model and value chain of renewable forecasting. So we start from the top, from the data. That can be the data we measure at the wind farms, etc., or remote sensing like satellite images, sky cameras, and others. Then these data are used as input to weather forecasting models to produce weather predictions by institutes like Meteo France. And then the data plus the weather predictions are used as input to the power forecasting models to predict the power output of the wind farms, PV plants, and combinations, etc. Then we have a layer which is a layer of service, which is quite important. I can explain later what we can do with this. And these forecasts are used as input to tools which are used for power system management or participation optimization, the participation of renewables in electricity markets. So the idea was, so far, the research was done in silo, actually. We were developing models for weather forecasting, models for solar forecasting or wind forecasting. And then we were using optimization models for the applications. Now what we are trying is to link all this, actually, and have this kind of holistic approach. So one direction was to develop a method that permits to extract the value out of data through data sharing and data market concepts. To do advanced weather modeling that is and forecasting, modeling and forecasting adapted to the energy sector, because so far the research of the weather institutes is oriented to all applications because their clients are from different sectors, aviation, energy, etc. So we see that, well, they can focus and produce, let's say, products, forecasting products and models which are more adapted to the energy applications. And then the other direction is to develop forecasting models which by design not only are optimized to maximize the accuracy, but also to other properties like simplicity, resilience, robustness, and the value they bring to applications. And this is a kind of new paradigm. And then finally, to develop a new generation of AI-based tool that simplify the decisions that we can take, and simplify actually the way that the end users use the forecast and all the information that we provide to them. So I will skip this. Some highlight results or directions. So one objective we set was to work towards what we call seamless forecasting. So I explained before this paradigm for solar forecasting. Usually the operators, etc., the end users need multiple models for different time scales, and so multiple forecasts for different time scales. And today they have to maintain a lot of, as a function of the data, lots of models. So the idea was actually to simplify this process and have, instead of having multiple models, try to go to a modeling approach which is seamless, which is able to consider all the available data as input, to be probabilistic, to be generic, to be able to handle wind, solar, or combinations, because now we have usually, actually, we manage more combined aggregations of wind and solar, and cover all the available time frames. This is, let's say, an objective we have fixed, a challenge. And in this project we had, and also in some PhDs, etc., we had the first publications, and they were quite interesting, and this is an activity also that continues.
What would be the longer time scale?
Well, actually, the longest time scale is defined by the horizon of the numerical weather predictions. It can go today up to 10 days. After that, you change the applications, you go more to seasonal forecasting, and you have other inputs, so we are not in that scale action. But a typical for the operators, because 10 days is mainly for specific applications like predictive maintenance, scheduling, or hydro scheduling, etc. The typical applications go up to, let's say, a day ahead or 2 days ahead. Yeah, so I skip this. Another objective we have fixed was to develop models, forecasting models for different applications, not only renewable, but also for demand forecasting, etc., which are, let's say, resilient to missing data or problematic data. Today, this is something very common, actually. We use a lot of data as input, and this data, especially at a local scale, they are not always of very good quality. Once we were participating in a project for a smart grid project where we developed a model to predict the demand at smart homes using smart meter data. And we had, at laboratory, we developed the model using historical series, which were very good, very clean data, etc. But when we installed the models at the demonstration project, we had a surprise, because 10% of the smart meter data were missing, actually. So the model that we developed in ideal conditions in the laboratory did not work. So there we had to develop what? Okay, with some kind of fallback models to say, okay, if the weather predictions are missing, then we apply this model. If the smart meter data are missing, then we take the data of the neighbor. If the neighbor does not have data, we take the consumption of the previous day as forecast. And anyway, so it was a kind of hierarchical approach. But this, if you go to more complex applications, you can have, it's a combinatory problem, because you can have lots of, and if you have a lot of input futures for different sources, you can have a lot of combinations of data that are missing. And this is not possible to apply this kind of chain of fallback models. So we try to apply robust optimization, so that to train the model to, let's say, understand what is, or to optimize the response as a function of the data that are missing. And then here we have some example to go to something technical, that for example, if we have, here is for solar forecasting, if we apply, if the method is random forest, which is a quite commonly used model for renewable forecasting, then if we don't have missing data, zero missing features, then we have a mean absolute error average for 24 hours ahead in the order of 5%. Then if we start to have missing features, input 1, 2, 3, etc., we see that the performance degrades actually a lot. So we can go up to 25% error, which is a lot. Now, if we have the possibility to train a model for each combination of missing feature, then actually we are in this situation, retrain, and then we can optimize the performance as a function of this. But this is impossible to do. It's very theoretical, because you have many combinations and the effort is huge, and you cannot implement operationally this kind of models. So this is the kind of reference case. But here we propose different approaches which permit actually, and this is the one that proposed in this paper, that permits actually to control the error, the loss of performance we can have, and at the end go to a performance which is very close to the retrain approach. And this is much better performance than the case of the classical practice where we apply a model and then we observe its performance without doing anything actually. Similar results were for the case of wind. So, now I will present some other concepts we worked, and there are some papers. I present here a typical model chain of an aggregator. Like in France, we can have, for example, a Compagnie Nationale du Rhône, that they manage a portfolio of wind farm and solar plants, and they valorize the production to the electricity market. So every day there is a trader who uses forecasts and take decisions how much he will participate at each market, day ahead, intraday, ancillary services. So to come to these daily decisions, you have to apply this model chain. So first you have the data, then you have to predict to have probabilistic forecast of the aggregated production of the wind and solar. So for this you need one model, but then this is not enough. You need also to forecast the prices of the day-ahead market and the intraday market. So for this you need, and also the imbalances. So here you have 3 models. And if you participate to the ancillary service market, you have another 6 quantities. And then in total you have to make 10 forecasts, which are used as input to a stochastic optimization model for trading. And this decides the bids for participation to each one of these 3 markets. So we have a model chain of 11 models actually. So this is represented in a generic way here. So we have the data. The data is used as input to the forecasting models. Here are the 10 forecasting models, and these are used as input to the decision making. So the classical approach in the state of the art is to optimize the performance of each forecasting model as a function of the accuracy. We make a prediction, we observe the real production of the renewable plant, and we try to minimize this error. However, we saw that in some situations, these models, for example, for renewable, actually the most performant models are generally the models that minimize the RMSE, etc. But here we have probabilistic forecasts, and in some situations we saw that the optimal strategy for participating in the market is not necessarily to participate with mean, but maybe with some lower quantile of the distribution of the probabilistic forecast or higher. But how can you decide for this? So what we try to do is to develop an approach which actually we do the tuning of the forecasting models not only based on the accuracy, their output here, but also considering the value, the impact they have to the decisions, the impact the forecasts have when they are used for taking a decision. So this is what we call value-oriented forecasting. So here is actually a tuning of the models, which is based on an objective function which is combined. It takes into account, on the one hand, the forecasting error, and on the other hand, the revenue that's generated at the end of the process when we participate in the market. And when we do this, actually we can say, okay, why not to do this? I mean, today we have in-hand methods based on artificial intelligence. Why not to try directly to learn the decisions from the available data we have and to replace all the forecasting models and the optimization step by just one model? We have tried this some years ago in a first thesis with the application of artificial neural networks. And the results were very promising because we saw that they were able to learn this policy actually. And then later on in this thesis, we applied methods of AI which are more interpretable, like prescriptive trees. Because here, okay, we replace a chain of models, but we don't want either to have a black box here. We wanted to have a method which is quite interpretable. Interpretable, what does it mean? It means that we have the capacity to link the decision with input. So to know why we take, or have some information why we take this decision, actually. So this is a prescriptive approach. In the literature, it appears as decision-oriented learning or end-to-end learning, and it's a kind of area which explodes today. And there are lots of applications. We can see that, okay. 5 minutes, okay, thank you. We can see, okay, that if here we can have, for example, total profit, and here we can have the classical approach, forecast and optimize, and then the prescriptive approach. And we can see that, well, as a function of the risk of the operator, we can come to a situation where the profit can be higher when we apply this prescriptive approach than the classical analytical forecast and optimize. And here is an analysis based on Shapley values that shows the well, the link between the decisions, the performance, and the input, actually. I will not. Some other directions is to try to, also in the interpretability of AI, is to apply what we call symbolic regression. It's an area we have explored, where the starting point, actually here, the objective is also to trade. We have a wind farm, and we want to trade this to the market. But we don't want to apply a black box model. So what we have here is, the starting point is a library of expressions that we know, for example, is wind speed in the cube, or temperature, etc. And then we apply a method of the symbolic learning with an optimization based on genetic programming. And then the outcome is a trading strategy which says, okay, when we forecast a wind speed between 1 and 3, the trading, the market will be analytically expressed by this relation, 0.05 wind speed at the square. Or when we are at this area of wind speed forecasted between 2.5 and 7.5, the trading will be given by this expression, and when we are in this area, by this expression. So what we try to do is, okay, to have a kind of a priori interpretability, to have a model which is by design interpretable. What we see very often is that we have a neural network, and we apply some post hoc methods to, like Shapley values, etc., to analyze the interpretability. But now what we try to do is to explore the possibility to have it by design, actually. And the last aspect, which is very, very interesting, is what I mentioned. We show that if we have a geographically distributed wind farms, we can use them as sensors and use them, their data as input to predict, to better predict the output of a single wind farm. So we saw that, for example, if we have wind farms in an area of 100 by 100 kilometers, then we can improve for the next 6 hours ahead up to 20%. This is without doing anything, actually, just by sharing the data of the other wind farms. The problem today is that we cannot share, in general, this data because they belong to different wind farm operators, and they have commercial value, and they don't want to share. So now what we propose is actually to, instead of sharing the raw data, to encrypt them and share the data, not of the raw data, but some proxies. So we are in the area of what we call privacy-preserving data sharing. And then we use some federated learning to execute the forecasting or optimization function, actually. So, and here, well, we have a PhD ongoing, and there are some methods like, for example, to add some noise in the data, or to have some methods of differential privacy. But There you lose some information when you add noise, etc. But here we managed to develop some methods where when you do this kind of encryption, you don't lose information when you share the data. And of course, what you have to prove is that you cannot, the inverse optimization to retrieve the initial data. This, in the frame of Smart Forest, we had the first solutions, etc., which the work continues. And we went one step further because the question, okay, we share the data like this. We have an improvement up to 20% for 6 hours ahead. This translates to benefits, higher revenue when we participate in the intraday market. Okay, but the question is, how do you share this value which is generated? So we developed a new concept which is a data market actually, which permits to valorize the data we share and to share them in a securized way, and then to redistribute the value that's generated. So beyond the energy markets, we can have the data markets. And actually, this is something today, after the end of the project, is the solution is implemented and is going to be applied by Elia, the system operator. And also there is high interest also for other applications like industrial basins, etc. I think here, okay. So just to go through very, very quickly, the challenge is that, let's say, as a community of researchers working on forecasting, etc., we have identified is first, it's important to continue the efforts on weather forecasting towards in a direction which is adapted to the needs of the energy industry. It's important also to continue research and developments with some ultra-high resolution models like large edge simulations for weather forecasting that can go down to 50 meters. Normally, the weather forecast today, we have a spatial resolution of 1.5 kilometers, but with this kind of methods, we can go much higher solution. Then to improve longer time scales like seasonal forecasting and associate uncertainty. There is a need to improve forecasting of extreme situations like ramps, fog, snow, icing, lightings, etc. Today, as I said, the technology is quite mature, but still in 10–15% of cases, the errors are quite big. Then it's always, given that we have more and more data, it's always a challenge to try to develop methods that combine all the sources of data. We saw before in the presentation that already when you try to exploit the data from cameras, then you have lots of challenges. I mean, what is the projection system, etc. So what happens when you try to combine this data with other data that can be useful? Then a very big problem is that for renewable and renewable and also demand forecasting, that so far the models are based on measurements which reflect the power production which is driven by the wind or the sun. Okay, and this the AI models are able to learn because there are these regularities, etc. But today there are more and more constraints because of environment, etc., that make that we modified the production of the power plants or the demand. So we can, for example, in the evening, we can reduce the power of a wind farm because of noise. So what we will measure in the night hours will not be what is driven by the wind, but what is controlled due to the noise. We're discussing with an operator of wind farms, and nowadays the new wind farms, they have to respect regulations regarding, for example, birds, collision of birds, to reduce this. And they are obliged, the new wind farms, by regulation to install systems that detect the birds, which are cameras They make video, and then you have AI, they detect the birds, and when they see that a bird is coming, they stop the wind turbines. But of course, we don't know if the bird will go to the wind turbine or not, because so what happens is that for one wind farm, they observed in 1 year 12,000 stops of wind turbines because of birds, because these systems are not very performant. So this reflects 10, 15%, 10, 12% reduction of power. But again, what we observe has nothing to do with the wind. So it's what you measure is at this time series, and then you try to develop a model behind. But how can the model know that you have all these up and downs because of birds? I mean, this is not an input to the model. So nowadays there is a big challenge to adapt the forecasting model to take into account all these external constraints that can be curtailments due to problems to the grid, ancillary service provision, noise, birds, etc. And there is another list, but anyway, I let you see in the slides the second part. So thanks a lot for the attention.
Thank you.